Hi guys. So this is not going to be brand new material that you only see in the lectures. This is going to be a review of what we've been talking about in classes, but I wanted to have it documented in a video format for you guys' reference. So I want to review what we talked about concerning the tables. So I just call them the tables in the back of the book. Some people call them steam tables, and they are lookup tables for thermodynamic properties. Some of those properties we've discussed, and some of them we have yet to get to. But remember that the big three things that we've been talking about are pressure, temperature, and volume, specific volume, because we want the intensive quantity. So we've been deriving and talking about these properties in terms of this surface right here, which we call the PTV surface. Whatever order you want to put those in, all right? Because this surface defines the properties of a liquid on a three-dimensional graph where this is pressure, this is specific volume, and this is temperature. So we've discussed this and the idea that all substances, although the shapes are a little bit different, have an equilibrium state that lies somewhere on this surface as defined by a three-dimensional shape. Now, we've also talked about the mathematical idea that when you have no surface and you just have three-dimensional space that is completely empty and nothing to go by, if you want out three pieces of information, let's say an XYZ coordinate, then you need to put in three pieces of information, okay? I need to give you three things in order to get out three things. And that's about as specific as I can be. There are mathematical ways that I can maybe tease out three other pieces of information than what you give me, right? So I could maybe put in not necessarily X, Y, and Z, because otherwise why would I get them out? But I need three things. That's the point. Three independent pieces of information have to go in to get this out. But the surface itself allows us to get out an XYZ coordinate only having put in two pieces of information. It's as if that surface serves as the third piece of information in itself, okay? That's in a mathematical sense what it's doing. So if I know a surface, I can just put in two properties and get the rest out. And this is the principle that we've already discussed in this class. We just need two independent properties to specify the state. So anywhere on this surface, if I want an equilibrium state, I can specify along one axis, along another, and then simply come up, like in this case, I might use an example of the pressure. I would specify volume temperature and come up to meet the surface. And wherever my point meets the surface, I've just gotten my pressure. So that's an example of how this works. Now, if I wanted, I could take this complex shape and think of it as being gridded up into points. So I'm going to draw these points as big dots, and you get the idea there, and we can put some dots down here, dots going up there, dots. There's like a curve here, and there are dots all along it. There are dots here, coming across all these curved surfaces. So every point on this surface is gridded up into these little dots, these little points, okay? And this is the physical interpretation of the steam tables, because every single one of these dots has associated with it. Let's call this dot number 1, okay? That's the first dot in our chart. It's got pressure 1, temperature 1, and specific volume 1. All right, let's call this one next to it dot 2. You guys get the idea? The This is different information, pressure 2, temperature 2, and volume 2. And so every dot is at a different coordinate and it has associated with it different coordinates. And so in the back of our book, when we see a table, the information in these cells of our table, this is like looking at one of those dots on our chart. That's what we're getting. We're getting some information about the coordinate from the table. So that is essentially what we're doing in our lookup tables. Now, I do want to touch on the concept in our lookup tables of the two columns that we find under the specific volume. So we see, and I'll raise the board for this. We see in our tables sometimes that we have a column that says VF and VG. Okay, and then there's other stuff. But those are specific volumes. This VF right here, the F means fluid, and this is called the specific volume of a saturated liquid. They call it liquid, F for fluid. It's a little bit inconsistent, but I could write that over here. So VF specific volume of saturated liquid. And Vg is the specific volume of saturated, G is for gas, but they're going to call it vapor. So you can call it either, really. I don't care. This one you can call fluid or liquid. This one you can call gas or vapor. It's all right. I'll know what you're talking about. It's just saturated vapor. Okay. So these are the definitions of these two things. And what they correspond to are the 2 points on the volume axis where, for a given temperature, you hit these transition lines, right? So if you follow this down, here is VF. The line where this mix becomes purely fluid, right? On this side of the line, we're only fluid, and here we're saturated, and that's what the point is. And then after this, we start to mix, and we're in a mixed phase in here. Over here is pure vapor. So we hit this line, and it defines the boundary along this saturated vapor line. And so this is what defines Vg. So it's a pretty simple concept. There's one other thing you'll see, which is what the width of this interval is, okay? Because that's something that we've talked about, how the shape is a little bit different for different fluids. Well, that can be something that has a little bit of a different shape. And so it's an interesting property to know and have a label for. So the width of this, well, if you think about it, that's a terrible bracket. If you think about it, the width of this is simply given by Vg minus Vf, right? That's all that is. So I can define a new thing, which is called VFG, and this is Vg minus Vf. So that, if you see this as one symbol, is shorthand for this subtraction. Okay, it's like just giving it a little bit of a nickname. And that's what VFG means. VFG tells you the width of that band, all right, for whatever given temperature you're at. So it is really interesting how they define where you are in the mixed state, because up until now we've just said our point is somewhere here. It's somewhere lying in this mixed state. But how do we really know? How do we know if we're more toward this side, more toward that side? And so, like I said, I think it's really interesting. What they do is they assign it a percentage from 0 to 100%. It's like a spectrum that you move across. So if you're right here at VF, you get a score of 0. And if you're over here at VG, you get a score of 100, and we can throw in like percentages like that. So really, it ranges from 0 to 1, because 1 is the way to write 100 without the percent sign. 100% means 1, okay? So it goes from 0 to 1. And that quantity, the name for that variable that fluctuates, is called the quality. X is the letter that we use for it. Has nothing to do with displacement or anything that you've seen from previous physics classes being X. This is X in a thermodynamic sense. Lowercase x is the quality. And it goes from 0 to 100, and it's valid only in the mixed state. Or mixed phase, I guess I could call it. So what I mean by that is that once I get over into here, if I have a state that's over here, which is purely liquid, it doesn't even make sense to talk about what's the quality of that. Or over here, in the purely vapor state. If I say I have a liquid that's totally vapor, what's its quality? I'm asking a nonsensical question. Quality only exists in this region. That's all it's for, all right? So, the definition of the quality is it's defined in terms of the masses of the two substances. So how much mass do I have that's made up of vapor, right? Because as I get toward the vapor side, I increase. So X equals, let me erase this a little bit, the mass of the vapor over the mass total. All right? So think about this definition for a second, and think about it in terms of that value ranging from 0 to 100%. If I'm all the way at the saturated line, all I have is liquid. It's about to become mixed, but it's not yet. It's still all at liquid. So my mass of vapor is 0. So 0 over anything, I'm going to get a quality of 0. As I go through and get to the other edge, I have 100% vapor. It's just come out of the mixed state. So my mass vapor is my mass total. It's the same number on top and bottom. And so whatever number that is, it just becomes a 1 or a 100%. All right? And anywhere in between, it ranges across just like you think. It just goes across linearly. So this is a really fascinating concept, defining the quality. It's used for solving problems and for being able to communicate in the real world about like what substance we have. And so there's a couple of definitions that you could figure out from yourself coming from this, but I just want to do real quick so that I have a documentation of them for you, okay? So, first of all, notice that the mass total, I'm going to do MT for mass total, that's going to be the mass of the liquid plus the mass of the vapor. M fluid plus M gas, okay? That's how I'm going to get the total mass. That makes perfect sense. And then I do know also that the volume is going to be, this is big V now, volume total, and that's going to be whatever the volume of the fluid plus the volume of the gas is. These are two obvious facts. But now I can start to substitute. So right here, I know that for a volume, big V, well that equals little v times the mass, right? This is the definition of little v. If I divide the mass over, it's volume over mass, and that defines it. So this is just definitional. So I can plug this into this formula. So I get little v total times mass total equals little v liquid, mass liquid, plus little v vapor, mass vapor. Okay? All I've done is replace each term with little v times m. So next, what I can do is eliminate this volume of the liquid because that's not in our definition. So I'll replace it with the mass total minus the, sorry, it's the mass I want to replace. I realize I just said it was the volume. Mass total minus the mass of the gas. That's equivalent to the mass of the fluid. I'm doing an equivalent replacement there. Okay, and then I still have this. Okay. Now, I just divide over by this mass total, and you'll see that out pops quality. So VT equals VF times, I'll write it first like this. Remember, all I'm doing is dividing everything on this side by the mass total to get rid of it on the other side. See what happens from that line to that line. Okay, and now our definition of quality comes in. So this becomes a 1. Mass total over mass total, that's 1. This here, mass of gas over mass total, that's our definition of quality. So this becomes X, and this as well becomes X. All right, so I will box this one up, because this is just a useful one to have handy. And again, this is stuff that if you wanted, you could derive yourself. It's just a little bit of algebra. That's just a handy formula. All right, and the last thing we can do is, I'll raise this up and keep going. Once I have this, I can rewrite I'm going to distribute, so volume of the fluid minus volume of the fluid X plus volume of the gas X, and group the X's together. Volume total equals the volume fluid minus, or I'll actually factor out that minus and put this one first. So now comes the minus, and that's all times X. So I factored the X out of that, and you'll see that this thing is what we have that shorthand for, volume of fluid gas. Oops, that's a plus sign, times X. This is another one. It's a handy formula to have just in your back pocket to be able to pull out in a calculation. It's just using this shorthand notation. And then finally, I can derive a formula for X in terms of the volumes if I want to. So the last one is that X is total specific volume minus fluid over VFG. And this one is certainly very useful.